Welcome back to Element 14 Presents. I'm Clem, and today we're adding multicolor support to any 3D printer, but we do it the open source style. Of course, we're not just taking an open source design from the internet and just build it. No. We take an open source design and iterate on it and contribute to the project. So we take the 3D Chameleon, which is a proven design that just works very well for adding multi-support to any 3D printer. But we're remixing the hardware completely, we're adding a few new features, and we're porting the software. So that means you in this project see all the steps that it takes to turn one thing into a different open source thing and contribute to the overall project while making bespoke hardware that perfectly fits your use case. The 3D Chameleon consists of two parts. You used to get this as a kit or maybe even pre-built, but to my knowledge they don't sell it anymore, but the files are now fully open source so you can build your own. This basically is the actual hardware that deals with swapping out filament paths and stuff. These parts in here move. This is the part we're not going to change. This is basically the mechanical part of the whole thing. And then there's an electronics enclosure, and that's what we're focusing our development efforts on. To build the mechanical part of the project, I had to source all these components. There are a few screws that you need, some specialized bearings. These are not like the normal skate size bearings, these are a bit special sizes, and a particular type of springs. I could only get most of these in boxes with like sets of components. For example, for the 8 springs that I needed for this unit, I had to basically buy a full box of various springs to get the particular size. I heard that sourcing these in the United States is a lot easier than in Europe, but you can still get them and it wasn't so hard to do. For the actual electronics, I need to find some parts that I want to use. And it turns out that the parts that they used in the original version, it's basically an Arduino Uno in a different form factor with bespoke things to plug your stepper motors and stuff in. So it's directly based on an Arduino Uno. And the chip that's on there is pretty much NRND, so not recommended for new designs. It's running out. So I'm porting over the project to a different chip that I have somewhere here in my hoard. Where is it? Instead of an 80 328P, the core chip of the Arduino Uno R3, I'm using an ATtiny 3226. This is one of the modern UPDI programmable chips by Microchip. It pretty much has very similar features to the old chip, but it's cheaper and easier to get nowadays, and I do not need an external crystal, and it still runs faster than the older one. So that could give me a bit of an advantage in adding new features, which I will gladly do. There are a few changes I want to make in my version. First, the microcontroller obviously, but also I want to have active cooling. Why do I need active cooling for such a simple two-stepper thing? Well, there are stepper motor drivers involved, and I will also upgrade these to TMC 2209 steppers. And that comes with the caveat of having to make them run perfectly cool. I don't like to get my electronics heated up within a heated enclosure. So if you want to mount, or if you have to mount all the electronics for your 3D printer inside a bigger enclosure, maybe if you want to print ABS, for example, then you should make sure that your components are kept cool. Oh, and the most important thing, the electronics were basically designed to be professionally produced and then sold to somebody who would then install it on their 3D printer. My version is made so you at home can assemble it yourself with just a soldering iron by hand. So I'm basically making it a little bit bigger. I'm adding new features as well, but I also make sure that it fits a specific case that you can readily get and easily modify. So you have a solution that is easier to experiment with, especially if you want to add features and develop new software for it. so you have an easier time accessing all the ports, measuring stuff, and keeping everything cool and still in a sturdy, nice container. So I'm making it fit a Hammond 1455 series case, which is very common and great to just slide in a PCB and have inputs and outputs on both sides. Enough preparation, let's head on over to KiCad and inspect the original schematic and then how we translate that into our new design. Open source projects are often published in the form of repos. This, for example, is the 3D Chameleon repo on GitHub, and we're basically looking through the files to see if there's enough for us to replicate the project at first, and then we'll basically translate it into a new version. So we're mostly interested into the electronics. So in here, we find a PDF of the schematic. That is pretty interesting. So we now have to identify how this thing works and then translate that into a new KiCad design. I've moved to the other side to give you a better view on the whole PDF. So what we have here, 80 mega 328P, that's the main processor like on the Arduino Uno, and it has a 16 megahertz crystal, so it basically acts as a normal Arduino. We have these limit switch connectors. This is the programming header. This just seems to be decoupling and the power LED. Extruder and selector stepper motors are connected to these drivers here. These seem to be DRV8825. It's not the oldest one, but it's one of the oldest Steptic modules. This is just some 7805 power regulation, and that's it. Here's the DC in port. Well, I think there are a few things we could add to this. So let's hop on over to KiCad and implement a few of these features. Now this is my new schematic. I've changed the microcontroller to an ATtiny3226. The S variant basically is SOIC, which means it is an SMD part, but it's one with big pins, so you could technically hand solder this still. We can see we have a lot of connections to the outside world here. These are all marked with these numbers here. These are the Arduino pin definition numbers that I got from the Mega Tiny Core, which I will use to program this chip with Arduino. So the pin numbering in the software is different to the hardware definitions and different to the pinout. So keep that in mind. I always mark these with the numbers in the Arduino IDE, and these int means interrupt and PWM means, of course, PWM. So I mark the capabilities of these pins at these pin numbers. If it only has a normal number, it's just a digital pin. These are TMC2209 stepper motor drivers in the same Polulu breakout form factor, the silent step sticks that we all know and love. But I've added this diode, which implements a feature that is usually on the silent step stick stepper protector boards. It's a Schottky diode that makes sure that the voltage for the logic is present before the 12 volts when this chip boots up. This makes sure that the chip can automatically detect its voltage reference level and then goes into the right mode. If that wouldn't have stabilized before we get the water voltage, then we could run into some boot issues with these. We need to put this into the manual mode and not UART configuration. That's why we have this pulled up. These are our normal enable step direction signal, just as on the original boards. These are the motor connections. They are broken out to headers, and we then associate in the footprints different things to these headers. So I'm using just a generic connector footprint because I then can dynamically decide if I want this to be screw terminals or like ready-made cables for plug-in, or make it just solder connections or pin headers or whatever I want. Or completely proprietary connectors. Could be anything at this point. It's just about the number of pins. Then we have our fan control and thermistor. This is our new feature. So this thermistor just builds a voltage divider between 3.3 volts and ground. We read that with an analog pin. And fan, of course, needs a PWM capable pin. We pull it high to make sure that the default state is deactivated. And then we control this via PWM with an RLZ44N. You may know that MOSFET from your 3D printer, because that's the same one that is used on the ramps and countless other 3D printer control boards for, I think, almost decades now. Very good MOSFET, logic level MOSFET, can be activated with 3.3 volts. I love this traditional part. Don't call it old, it's a traditional part. These are our user LEDs. These are not mounted directly onto the board, but their legs basically extend to the front so they can be positioned above all these headers. And they span the whole side of the case. And now you know why I specifically use a Hammond 1455 case, just so that I can fit all these connectors snugly in here. Don't have any wasted space. I could use a more shallow one. This one is very available and is one of the cheaper options, so I think it's a good trade-off between size and expandability and ease of soldering. There's always trade-offs, but this one should be a bit easier to assemble by hand than the original version. Thanks to our glorious friends at Eisler, I get these PCBs professionally made. I call it the 3D Brucasia, because it runs on an ATtiny and Brucasia is a tiny chameleon. And it's based on the 3D chameleon, so I thought that was a fitting name. So now we have to stuff all the components onto this and make it work with a bit of code. I won't bore you with the code in too much detail, but it's pretty simple. We are porting one software from one platform to another. This means, in its essence, we're making sure that all the stuff that works on the old board also works on the new board, which means first we have to change all the pin definitions to the new pins. We didn't have to restrict ourselves to the same pin numbers, but the same pin capabilities. So if a pin has to be able to output a PWM signal, also the new one has to be capable. Same if you use an interrupt for something. The new pin has to be interrupt capable, I2C has to be on I2C capable pins, you get the idea. So we change these pin definitions, and we may have to substitute a few libraries and stuff. In my port I also removed all the I2C specific features because the unit is actively searching for those I2C devices. On startup it won't find them and then it won't go any further. So we're removing all of these as long as we don't have any of the I/O expander or screen capabilities installed. We don't actually need them. So I'm making it always as simple as possible in the first version just to make sure everything works. Once it behaves like it should, then we're ready to add more features. The first feature I add is a temperature controlled fan. For my demonstration, I just keep the target temperature at 30 degrees C. In my room, it's slightly below, and if I touch the NTC thermistor, then I would basically raise that temperature with my body temperature, and you can see the fan will engage. Turns out it doesn't when I just try that, and turns out I should listen to myself, because on the board it says tab facing up on the MOSFET that I use to drive the fan. And the tab is facing down. So if I would have listened to myself, I would have assembled the unit correctly. So we have to do a little bodge, but then we can enter some code to make that one work. The code is fairly interesting. Basically what you're doing is you're building a voltage divider with a thermistor and a known resistor. Now, with the known voltage divider formula, you can determine how much that thermistor resistance has changed with changing temperature. That influences your analog reading on your analog pin. How do you know how much that changes? Well, there are formulas and there's a thing called the beta coefficient. You will have to know that for your specific thermistor. You can usually find that in the data sheets or Google around. Maybe somebody has already posted that on the Element 14 community. That's the place where I usually find these things. For my LEDs, I'm doing a little bit of a different activation scheme than usual. You could just digital write high and low to activate or deactivate an LED, or do a PWM signal on there to make it fade. But I'm more interested in knowing which extruder currently is active. And that means I just want to have a number between 0 and 4 active LEDs. So I made a function called set LED count, which means you just give it the number of LEDs that should light up, and it does the rest. So we can call this function from everywhere in the code. That keeps it really clean, and if you have to change something about the behavior, maybe we want always these LEDs to fade up and down when they change, then we just have to change that one function and don't have to search for every LED activation or deactivation that we have in the code. This makes for cleaner code at the expense of a bit more programming effort. But the loop does the most important thing on the 3D Chameleon. It basically checks for a micro switch that is pressed or not. And if it's pressed, it will count basically the seconds it's pressed. And depending on how long you press it, it will activate a different function. So what I basically can do with my finger, the 3D printer can do by just running its extruder head into the micro switch. Which means you don't have to directly interact with the electronics of your 3D printer. All it does is letting the 3D printer activate an external device to change the filament. So the only change that you do is in the G code that you give the machine, because it has to know how do I change filaments. And so basically what 3D Chameleon provides is a G code preprocessor, or it's an after processor. Basically it adds in specific sequences at these color change events in your G code, and that basically tells the 3D printer what to do and how to activate a specific color. You can tell how many seconds have passed when you press this thing, because the microcontroller makes the motor vibrate while it calls. This is a great idea. I love this way of tactical feedback. Don't have to have any screen or whatever, and it tells you how many seconds you have actually pushed the switch, so you can just count and then it does your bidding. I added the LEDs because after you have counted, do you remember still on which extruder this thing now is, especially if you're currently just loading filament in and not running G-code actually? Well, I lost track a lot, so the LEDs help me. I put them in all the sequences in the code whenever basically, usually you would write something on the screen about which extruder is used. I just light up LEDs in that case. That's all I did. Our freshly assembled electronics are ready. I've added a little bit of lettering to tell me which of these plugs go to which section of the board. Yeah, I should also have that in the 3D printable design, but I couldn't be bothered. That was faster to pull off. But you can see I have headers on the outside that make it a lot easier to swap around cables and stuff during debugging or when I want to experiment with new features. You can power this with a 12-volt wall wart, or you can just wire it directly into your 3D printer's power supply. So you only need one. It's just 2 extra stepper motors. 1.5 amps is plenty enough to run this. I'm not running you through the whole installation and loading process. It's the exact same like with any 3D Chameleon. Links on the show notes, but we're connecting these two things up and I'm showing you how it actually works, like how you give commands and then the filament actually changes and loads in and whatever. So this is pretty cool to see. We did it, folks. We contributed to an open source project by remixing the electronics, porting the software, and I hope this inspires you to give it a go yourself. Make your own bespoke version of an open source project you like. Big thanks for open sourcing this project to the original creators, so it gives me the chance to remix it and share it with the community and have my own bespoke version with some new features. And maybe you have some ideas for even more features that could be bolted onto this thing. Let me know on the Element 14 community. This is also the place where I can download all the files, and I will of course push my new version to the GitHub, to mine, and then make a pull request to the original repo. I gotta go. There's another project waiting for me.